Hi, I'm Charlie Fitz, author of Anaqsim. Welcome to this Anaqsim in-depth video series, and thank you for your interest in Anaqsim. The aim of these videos is to help you understand Anaqsim and how it works at a deeper level so that you can more easily apply it to the situations that you want to model. In this session, we will cover what an analytic solution is. We'll cover the basics of the analytic element method and how the AEM compares to numerical methods. And we'll finish with some resources for learning more about the AEM. Let's first define what we mean by an analytic solution. Mathematical models of groundwater flow obey two principal math equations. Darcy's law, which relates head gradient to hydraulic conductivity and discharge, and conservation of mass. Those two mathematical constraints can be combined together in a general differential equation that looks like this top one, called the general flow equation. And in that, H is hydraulic head, X and Y are the coordinates within the two-dimensional plane. This is a general flow equation for two-dimensional steady-state flow in an isotropic homogeneous medium. And mathematicians know this equation as the Laplace equation, and you've probably seen it in textbooks on groundwater flow. An analytic solution is an equation that satisfies the general equation perfectly. And the second equation here is an example of an analytic solution. You can see that if you differentiate head with respect to x, it becomes a, which is a constant. And if you differentiate head with respect to y, it becomes b. If you take the second derivative of a constant, you get 0. So both terms in the general equation work out to be 0 for this particular solution. And in this solution, x and y, again, are your coordinates within the plane. A, b, and c are constants. Turns out A is the hydraulic gradient in the x direction, B is the hydraulic gradient in the y direction, and C is a constant that raises and lowers this planar surface, sloping surface that would define a uniform flow, that the discharge is the same everywhere in the xy plane. So that's an analytic solution for uniform flow, and it satisfies this general equation perfectly. Something like the analytic element method has been around for a long time. People have derived analytic solutions to the general equations of flow and applied them directly, and then gone one step a little further in the direction of the AEM by superimposing multiple analytic solutions. What I'm showing here on the left is the analytic solution for radial flow to a well in steady state two-dimensional flow. Capital Q is discharge of the well, capital T is transmissivity, R is radial distance from the well, and C is a constant. And here's that solution. You've got blue stream function contours or path lines and black dotted contours of head, and they are normal to each other, as you'd expect. You can superposition two of these in what we call the method of images on the right to simulate a flow field for a well that's near a long, straight, constant head boundary, which occurs on the bisecting line. Quite useful. So these things have been around since the early 1900s, even the method of images in this application in particular, wells near long, straight boundaries. Computers, when they came along, allowed us to superimpose very large numbers of analytic solutions. In the thousands or tens of thousands are possible now. The computer programs that have been written automatically assemble and solve these large systems of equations. And another thing that helped the AEM was the derivation of analytic solutions that are more sophisticated for lines, curves, and areas, not just point sinks. The lion's share of credit goes to Dr. Otto Strack at the University of Minnesota. He was my PhD advisor, and he wrote a book in 1989 called Groundwater Mechanics that summarizes most of the AEM key parts of the AEM theory. And most developments in AEM were either his or his descendants, which would be his grad students or students of his former students. Well, I didn't promise you there'd be no math, so here's a little bit of math. What we're looking at here is the general equation of flow that you get by combining Darcy's law with conservation equation. And let me define some terms. X and Y are your coordinates within the plane of the 2D model that you're developing. T is transmissivity, which is saturated thickness times horizontal hydraulic conductivity. L sub T is leakage out the top of this blue prism that goes from the bottom of the saturated thickness up to the top of the saturated thickness in a aquifer. L sub B is leakage out the bottom, and this third term here is the storage term, where S is storativity in a confined domain or specific yield in an unconfined domain, and T is time. So this equation is balancing lateral flows in and out the sides of the prism, which is on the left. That is the net lateral flow into the prism through the sides. And the right side here are the distributed fluxes out the top, out the bottom, and into storage in the prism. And those are set equal to have conservation of mass and volumes. So the analytic element method finds solutions, head as a function of x, y, and time, that obey this general equation. And then you can add those up since this is a linear partial differential equation. The analytic element method is generally written in terms of an aquifer discharge potential, written as capital Phi in most textbooks, and that is closely related to head. In a confined domain, it's linearly related to it. In an unconfined domain, it's linearly related to head squared. And the relationship between discharge potential and head is defined such that these first equations are true. The gradient of the potential is equal to transmissivity times the head gradient. And that's been successfully defined for confined domains, unconfined domains, and a variety of other kinds of domains that we'll get into in a bit. But when you have this definition that applies between the discharge potential and head, you can substitute that into our general equation here, and the resulting general equation now can be written just in terms of the aquifer discharge potential phi. And the sum of the second derivatives with respect to x and y is called the Laplacian, and this is a shorthand way to write that. And that is equal to those distributed sources on the right-hand side of our general equation. What we call elements in the analytic element method are actually mathematical functions, head as a function of x, y, and time, that are solutions of the general flow equation. And these can be two-dimensional functions in general. There has been some work on three-dimensional functions for analytic elements, but that gets to be quite cumbersome and difficult, so it hasn't really pushed forward into applications. But in 2D, we have fundamentally elements for point, line, and area sources and sinks, and these are illustrated below. Obviously, the point sink is useful for a well. A line sink is useful for discharge that's stretched out along a linear boundary, such as a reach of a river. And area sources and sinks are useful for sources that are distributed over areas. This here shows a green polygon, and inside of it we've got a high recharge rate, maybe it's a recharge basin, and outside of it there's also recharge, but at a lesser rate. The red are vectors, the blue are contours of equal head, and note that with the well and the line element here, the contours of head or potential, which these black dotted lines are perpendicular to the stream function contours or stream lines, these blue lines, and they form a perfect flow net where these are roughly squares, the intersections are at right angles, and so on. You see that both with the point sink and the line sink. That is not true of the area sink, though, where the source and sink are distributed aerially over the plane. Flow nets do not apply in that case. Here's how superposition works in an analytic element model. You have numerous solutions of Laplace's equation, which applies for both well and line elements, those where a flow net can be drawn. And especially the line elements, you may have thousands of those in a model to represent stream network or so on, and lots of wells that might be pumping. And if we take the Laplacian of that, which is the left side of our general equation, because they are solutions of Laplace's equation, the right side is 0 for all those elements. And we can add to that an area sink element where the right side is non-zero. It may or may not be a function of position, depending whether it is spatially variable or not, two different kinds of area sinks. When we add all of that together, we get a composite solution to the general equation that has on the left-hand side all of these terms that we're adding up, and on the right-hand side just the contribution from the area sinks. And that is hopefully doing a good job of approximating the leakage terms in and out the top and bottom of our domain, as well as fluxes into storage. Here are two examples of superposition of fundamental elements. The one on the left is showing 6 different wells being added together, but they're done in a very specific way that creates images about this circle that divides the gray area from the white area. And this could be useful for simulating the gray area, for example. Could be a model of 3 wells on a circular island with a constant head lakeshore. Or it could be a model of the white area on the outside of the circle, which would be a model of 3 wells located near the shoreline of a circular lake. On the right, we have line elements in green, line sink elements that are pulling water out of this aquifer, and then everywhere there's a uniform area sink representing recharge. And you can see quickly that this is quite useful to simulate regional flow and irregular boundary conditions. The analytic element method's mathematical model is basically a series of long equations where you plug in your x and y and possibly t for a transient model, and you get the discharge potential out. And discharge potential is related in a fairly simple way to head, so you can first get discharge potential and from that get head. You can also take the derivative of the discharge potential and get the aquifer discharge vector, capital QX, capital QY. That is closely related to specific discharge by the saturated thickness. So if you have the aquifer discharge vector, you can divide by saturated thickness to get specific discharge vector. And if you have that, you can in turn divide it by the porosity to get the average linear velocity vector. So you have these nice equations, long equations, with contributions from every element in the model, and you can get out the specific discharge vector if you're trying to trace a path line, or you could get out the discharge potential if you're contouring head, and it's quite convenient. Let's look at a simple AEM model and the equations that underlie it. This model shown right here is a homogeneous, single domain, steady state model, and It has a well in the middle that's pumping. These blue lines are head contours. It has a head specified line boundary on these three segments at the right. It has a normal flux specified boundary in the north and west that is letting water into the model, and it has a head-dependent flux boundary, which I'm tracing down here, that lets a bit of water out of the model. The mathematical model here is shown in this top equation. The head, as a function of location within the xy plane, is first evaluated in terms of the aquifer discharge potential, and that in turn is converted to head through the head to potential relationship, which is a function of the domain, whether it's confined, what elevations it has, what conductivities it has, and so on. The aquifer discharge potential function is a sum of contributions from a well, this one, which has known discharge. We've specified that, so there's nothing unknown about that term. And contributions from each of the line sink elements that form the outermost boundary. And each of those, at the outset, we do not know the unknown strength parameters that will cause these boundary conditions to be met. So there are, I think, 19 of those line sink boundary elements, and then there is a uniform area sink function that supplies a constant rate of recharge over the entire model area, and that also is specified, so there's nothing unknown in that term. And then we have a constant that is added to the entire solution. So these line sink contributions, each one has unknown strength parameters like U sub A here, U sub B, and U sub C. And it has known coefficient functions, which are a function of the line sink position and orientation, as well as the location of x, y. So Anaqsim solves for these unknown strength parameters, U, by generating boundary condition equations at control points on these line element boundaries. Take this right-hand boundary where we've specified that the head is equal to 104. On that boundary, there are control points marked by these little X's that I'm hovering near. And at each one of those, there's a boundary condition equation. I believe there are 5 per line segment here, that specifies that the head must be 104. And there are 5 terms in each line sink function and 5 unknown strength parameters, U, A, B, C, D, and E. In this case, because there are 5 unknown strength parameters, I've written out only 3. So Anaqsim has generated a system of 99 equations to solve for the 99 unknowns that go along with all of these outer line sink boundaries. And some of the equations are for specified head, some of them are for specified flux, and down here some are for head-dependent specified flux. So Anaqsim builds a system of 99 simultaneous equations for 99 unknowns, and it solves for them. And once they're known, these unknown strength parameters are known through the solve process, you can use this equation to evaluate head anywhere in the domain of this model, and these contours were generated by doing that at thousands or tens of thousands of points, and then interpolating contours through that data. And you can do the same for average linear velocity or specific discharge. Once you have these unknown strength parameters, you have an equation that gives you head or discharge or velocity at any point. Let's look at the system of equations that that model would conceivably generate. In this table here, or this matrix, I'm showing just the first 6 equations and just the first 6 terms in each of those 6 equations. They would each have 99 terms because that model had 99 unknowns. So it would keep going to the right for a total of 99 terms instead of just 6. The U's are unknown strength parameters. The D's are known constant coefficients that can be computed and are computed by Anaqsim. And the K's are known parts of the boundary condition equation. Each row here is one boundary condition equation. For example, the first 5 rows here might be the head-specified boundary condition equations at 5 control points on one of those line segments at the right side of the model, which were head-specified. And the known part here would be the specified aquifer discharge potential, which is related to the specified head. The D coefficients are computed by Anaqsim, and there's D11, D12, and so on, which apply to the first equation, but are different strength parameters contributing to it. So each element in the model contributes to the head at, say, this first control point where this first equation applies. So these D coefficients are all non-zero. If it had no contribution at all, then you'd have a 0 D coefficient. But because it's an analytic element model and every element affects every other element, these are non-zero in general. So you have what you call a fully populated matrix with the analytic element method, and that's just a characteristic of the method, and we'll see that is different than in numerical methods. Let's contrast the AEM and Anaqsim with numerical methods like finite difference and finite element. In both of those, you break the domain that you're modeling, the whole region that you're modeling, into small cells or elements, and then construct relatively simple equations relating the head at nodes within each cell or element to one another. And it's just an equation that relates one cell or node to its neighbor nodes. And in the simplest way of doing this, this is what was common in finite difference models up until just recently. This was the only option, was to define a rectangular grid of little boxes like this. And each box had a node at its center, and there were simple equations based on Darcy's law and continuity of flow that relate the head at neighbor nodes to the one at the central box. And so an equation like this would only have 7 unknowns in it, the head at the central box and at the 6 neighbor boxes. So it's relatively simple, but a drawback of all this is that you have to define a grid, and where the grid boxes are large, you have kind of poor accuracy of things. You wouldn't want to, for example, try to model a well in a great big box. You'd want a small box where the scale of the box is not too much different than the radius of the well, and that gets cumbersome to build in fine grid work right around each well or each important feature like a slurry wall or something like that. This is a mock-up of the system of equations for a typical finite difference or finite element method model. And each equation is written in terms of the heads, the unknown heads at the node itself and its 6 neighbor nodes. Here we're thinking about a rectangular grid, which each node would have 6 neighbor nodes. So in the long equations, they're mostly 0 coefficients, except for the neighbor nodes and the node itself. So these green boxes represent non-zero coefficients. And in this case, each of the first 3 rows I've put in the boxes to represent where it's non-zero, where those coefficients are non-zero. And in each of those 3 rows, there are 7 non-zero boxes. And that's because in a rectangular grid like ModFlow typically had done, there would be the node itself and 6 neighbor nodes in the 3 orthogonal directions. So what you end up with in the finite difference finite element method system are sparse matrices where most of the D coefficients are 0, and you have maybe 7 to 10 or 15 non-zero coefficients. You get to go above 7 when you have an irregular mesh, like triangle, finite difference mesh, or some other kinds of irregular meshes. On the right side over here, the K constants are the known factors in the nodal equation, and that might be something like the known discharge at a well node, things like that. In the finite element method and recently in the finite difference method, it has become possible to use unstructured grids like this. This one happens to have triangular elements as opposed to the rectangular grid like in the previous slide. And this does help with spatial resolution some, but again, it's quite cumbersome. You have to build special grid spacings around wells or trenches or surface water features like this. And then if you wanted to move the well or move this feature, it would require redesigning the grid and moving everything around and changing a lot in the inputs. So that's a little bit tricky. With the system of equations that gets generated, as I said on the previous slide, it's a fairly short equation with maybe only 7 unknowns in the case of a rectangular grid, and something probably a little bit longer in the case of an unstructured grid like this, but still enormous numbers of equations, but each equation is relatively short. And there's a whole host of numerical methods for solving those kind of systems of equations, which are called banded because a whole lot of the coefficients are zeros. And that does allow you to solve a much larger set of unknowns and build in more complexity and detail. So these kind of methods have their place, and it generally is in the most complex kinds of situations, but it's very costly to construct and maintain such models. This is a quick comparison of the analytic element method versus numerical methods, and on the left are listed pros of the AEM. And the first one is its geometric flexibility. Since you don't have to discretize the domain, there's no grid of boxes or a mesh of triangles. You only discretize the boundaries, not the domain itself. And that's much simpler and quicker to construct a model. The accuracy is better, especially near features like wells or barriers or drains, where the point elements and line elements in the AEM do a really great job, an accurate job. The inputs are much smaller and it's quicker and easier to build. It's also a whole lot easier to alter your model, change the location of a well or of a drain or something like that. And you have this continuous solution of head and discharge, so that makes for accurate path lines and accurate travel time calculations and transport and so on. The drawbacks of the AEM are that the kind of system of equation that it generates is a little bit sparse in Anaqsim and not sparse at all in most other AEM programs. And that contrasts with the numerical methods that have a banded matrix with a whole lot of zeros in the matrix. So the advantage falls to the numerical methods when you're trying to solve a system of 100,000 plus equations. That does not work so well with a fully populated or nearly fully populated matrix. Just takes too much time to solve that. And the mathematics with the AEM is quite involved and uses complex variables, and just a lot of detailed math knowledge is required to really understand how these solutions are derived. Although to be a user of the AEM, You don't have to know all that. But if you want to, it's a much easier task to understand the finite difference method or finite element methods mathematics. In conclusion, the AEM is best suited for models that range from the simple end of the spectrum up through moderately complex. Extremely complex, I think in a lot of cases you would be better off doing a numerical method, but I find that I almost never use a numerical model anymore. I haven't in the last 5 years of my consulting work because I can find a way to use Anaqsim at a moderate complex level to get really good insights into the problem in a fairly short time. So a little bit about model complexity here. Models are always going to be wrong. They're always going to be simpler than the real world. And the real world in the subsurface, we have very limited knowledge of. We may have a boring here and another one over there 100 meters away, and a third one 100 meters away from that. And that is very limiting. So we always have incomplete knowledge of what we're trying to model. So a simpler model actually is good in that it lets you experiment and try on a bunch of different concepts without having to reconfigure this beast of a model. It's a simpler and quicker model to build. And I think that the model you want is just complex enough to capture essential things in the problem. And you don't want it to be too simple where you have to leave out really key things like three-dimensionality if it's really a three-dimensional flow problem. And you don't want to go too complex because when you go overboard in that direction, it takes a lot of time and money, and you don't have enough data to calibrate the thing, and you don't have enough time to experiment with different concepts. Here are some reference books on the analytic element method. The first two are by Otto Strauch, the inventor of the method, and the 1989 one is a bit thicker and more detailed than the 2017 one, although both of them contain quite a bit of mathematics and theory behind it. The Heichema book is similar content to the Strauch books, only much leaner and a little more application and a little less theory oriented. The final reference there, my groundwater science textbook in either the second or third edition, devotes a couple of chapters to the basics of the analytic element method. Much less depth than those other three books because it's covering a lot of other topics as well. So it's just a good introduction to the analytic element method.